This is Module 10.08, Disrupting an Equilibrium System, also known as Le Chatelier's Principle. Le Chatelier's Principle says, when a system at equilibrium is stressed, the system shifts to relieve the stress. It tries to regain the equilibrium. What this means is the system tries to get back to the original equilibrium position, but it never can get all the way back. Today, we're going to look at three ways to disturb an equilibrium. First, changing the concentration of the reactants or products. Second, changing the container volume. This applies to gaseous reactants or products. And third, changing temperature. This is the only change that we can make that also changes the value of K. Otherwise, the equilibrium constant remains the same. So let's go ahead and write in there, K remains constant. Note, adding a catalyst does not shift the equilibrium. It increases the forward and reverse reaction rates equally. So let's first look at the effect of changing reactant or product concentration. We're going to look at the following reaction in a 2-liter flask at a constant temperature. We have nitrogen plus hydrogen reacting to make ammonia, and our delta H of reaction is negative 91.8 kilojoules per mole. K in this case is going to be NH3 squared. This should just be review for you over N2 times H2 cubed. Okay, so we're going to look at applying one stress in detail and then go look at the other ones in terms of concentration. So the stress that we are going to apply is we're going to increase the concentration of N2. So we were at an equilibrium and somehow we suddenly increased the concentration of the N2, injected a bunch in there. Now the system has too much N2. Our numerator is too large. Q does not equal K. So the system will shift to consume the excess N2. It does this by reacting with the hydrogen, and the hydrogen concentration will begin to decrease. As the nitrogen reacts with the hydrogen, we're going to see more ammonia forming. Eventually, the system will level off at a new equilibrium. Notice that the pressure of nitrogen has dropped, but it never gets back down to its original level. And once again, K does not change. So here would be a model answer for an AP exam. If the concentration of N2 is increased, the system shifts to consume the excess N2 and more NH3 forms. So shifts to consume. So what we're going to do is we're going to go through a table here for applying various stresses to the nitrogen, hydrogen, ammonia equilibrium. The system response, we're going to show which way the equilibrium shifts simply by drawing an arrow, and then we're going to talk about what happens to the concentrations of the various species. So we've already done increase in N2, that's what we just did. The system shifted forward. Now in this case, we increased this. This is something that we chose to do, and now we are looking at the responses. We saw that the hydrogen decreased, and that's because it reacts with the N2. We saw that the ammonia is increasing. And the impact on K, no change. Now, let's say instead, now we're going to increase the H2. So I'm going to write in here, we increase, so this is the change that we made. This is very similar to what we did the first time when we increased nitrogen. We increased the H2. Now there's too much hydrogen, so the system has to shift to get rid of the hydrogen, which means it's going to shift in the forward direction. The amount of ammonia will increase. The nitrogen is actually going to decrease because it reacts with the H2. Now let's increase the ammonia. So we increase. Now we have too much ammonia, which means that the reaction has to shift to get rid of ammonia. The reaction has to shift to consume ammonia. So we're going to see the hydrogen is going to increase and the nitrogen is going to increase. And impact on K, no change, no change. So this was increasing concentrations. Now let's look at reducing concentrations. So we're going to reduce the amount of nitrogen here. Now we don't have enough nitrogen in the system. The denominator is too small, so the reaction is going to shift to replace the missing N2. So we decreased. The ammonia is going to decrease. So it decreases to replace N2. As that happens, our hydrogen is also going to go up. So H2 increases as NH3, and in this case, that's a decomposition. Decomposes. Well, that's not fitting too well, but we'll squeeze it in there. All right, let's reduce the hydrogen. So now we're going to reduce hydrogen. So this time we're going to take the hydrogen down. So the reaction will shift to replace the hydrogen, key phrase. We're going to replace the hydrogen. So we decreased hydrogen. The ammonia has to decrease to replace the hydrogen. And the nitrogen is going to increase. The last thing that we are going to do is to reduce the amount of ammonia. So now we're reducing the amount of ammonia, which means that the reaction needs to shift forward to replace ammonia. When that happens, it's right in here, we decreased. When that happens, our nitrogen and our hydrogen have got to decrease in order to react together to produce more of the ammonia. So we have no change, no change, no change in our values of K. Okay, let's try some more examples on the next page. So we're going to try some sample essay questions. So we're going to try to use the right terminology that is expected on the AP exam. So the following system is at equilibrium. We have S8, I want you to notice that it is in the solid phase, plus 8O2 gas plus SO2 gas. Here's the question. Will the concentration of SO2 increase, decrease, or remain unchanged if we remove the oxygen from the flask? Justify your answer. So I want to pause the screen here, and you are going to try to answer the question. Okay, so you should have said that the concentration of SO2 will decrease if we remove O2. The SO2 will be consumed to partially replace the lost O2. So if you lose something, you're going to replace it. If you add something, you're going to consume it. Okay, so here's another question. Will the concentration of SO2 increase, decrease, or remain unchanged if we add S8 to the flask? Justify your answer. I'm going to tell you right off the bat, this is a trick question, because what I want you to do is think about what the equilibrium equation is here. S8 is a solid. So our equilibrium equation is SO2 raised to the 8th power over O2 raised to the 8th power. Do you see S8 anywhere in that equation? And the answer is no. So the concentration of SO2 will remain unchanged if we add S8 to the flask. So the SO2 will be the same if we add S8 to the flask, because SA is not part of the equilibrium expression. As long as we have some S8 in the flask, the concentration of O2 and SO2 will not be affected by how much is present. Okay, so let's try another one kind of along the same vein, but just a tad bit different here. Will the amount of S8 increase, decrease, or remain unchanged if we add SO2 to the flask? Justify your answer. So you might look at this one and go, well, S8 is not part of the equilibrium expression, but if we add more SO2 to the flask, what's actually going to happen is we will produce more of the S8 solid. So we can affect the amount of S8 solid, but the amount of solid does not affect the gaseous products. So the amount of S8 will increase if we add SO2 to the flask. S8 will increase as we add SO2, as the excess SO2 will be consumed. There's that term, consumed, and produce more S8. Okay, this next one here, effect of changing concentration by dilution or concentration, is more subtle. Consider the reaction HF in equilibrium with H plus and F minus. What will happen to the equilibrium position if more water is added to the container? Okay, so we're going to add more water to the container, which means all of the molarities decrease, which I'm showing by an arrow. Notice that the concentration lost most heavily impacts the side with the greatest moles of aqueous species. We're going to be multiplying two things by each other. If you've got two things that have gone down by the same molarity, you're going to see a greater impact. The reaction will shift towards the side with the greatest moles of aqueous species. This is always what will happen when you dilute. This reaction mixture will shift toward the side with the greatest moles of aqueous species. In other words, a larger percentage of the HF molecules will dissociate. It's just the opposite if the solution evaporates. All the molarities will increase. Notice in this case that we have two things increasing on the top and only one thing in the denominator. So the concentration gain most heavily impacts the side with the greatest moles of aqueous species. The reaction will shift towards the side with the fewest moles of aqueous species. So it's just the opposite. In other words, a smaller percentage of the HF molecules will dissociate. So if you run into this type of question, making these little arrows here can help you remember what's going to happen. Key: if you dilute, the reaction mixture will shift towards the sides with the most moles of aqueous species. If you concentrate, it will shift towards the side with the fewest moles of aqueous species.